Good morning, everybody. Hope everybody's doing well this fine Tuesday morning. It's a snowy day in Hamilton, Ontario today, and there's just a lot of ice everywhere. Looking out my window. Good. So, with respect to the Jupiter system, I think we're still getting everything together there. So we're not quite ready for the Jupiter yet, but don't worry. There's nothing due this week. Assignment 1 is due at the end of next week. This week is really just to get the systems online because it usually takes that long. But anyway, we're having a little bit of trouble with it. The way that the powers that be decided to do things this time around was to see if we could do some sort of a continuation. Yes, thank you, Mark. We were seeing if we could do some sort of continuation of all of the configuration from the previous semester, and yeah. So I guess I'll address the elephant in the room that Mark has just brought up. It's possible, if you guys have been sort of going directly to the lectures from the links that I've been posting to Avenue, that you haven't actually seen my channel page yet. But for some time now, I've had this announcement trailer for a video game that I made called Hexy Hashy, and it is a puzzle game. And I released it on Steam this morning. It's now available for purchase. This is just a small amount of shilling that I'm doing because, good Lord, Lord knows I don't get paid enough to not be expected to not shill on stream. So there you go. This is Hexy Hashy. If this looks like your jam, then you can buy the soundtrack too. It's got a really good soundtrack. It's got achievements. It's got all the stuff. Apparently, it's similar to Gris. I'm not sure how, but there you go. Yeah. I'm sure I don't need to tell you guys that the sort of the first week, the sales and reviews that come in the first week, or even in the first day or two, that really dictates the degree to which the game will enter into Steam's recommendation algorithms. So if you would like the game, please purchase it today and leave it a review. The user reviews are extremely important on Steam. But yeah, the first assignment was due January 24th. No, I don't think so. Pretty sure not. Set a new speedrun for A-. So no, I'm not offering any bonus points in the course for having bought the game. That's called corruption, and we're going to try not to be corrupt. I'll tell you it exists, but I won't incentivize you to buy it. It does look like Slices. Oh, that is a game. Oh well, it's called Hashiwakakero. It's a classic puzzle game that's actually designed by the same people as made Sudoku, but it's never been done before on a triangle grid as opposed to a rectangular grid. That's my unique selling point. Can I play it on stream? Well, actually, I was thinking that if I had time this afternoon, I would do a special non-course related stream on the YouTube channel. So if you want to get enough notification when that goes down, please subscribe to the channel. Can you get a discount? Well, you're already getting 10% off. How could you... Oh, and if you want to buy the complete edition, that's currently at 19% off. You can get the game and the soundtrack for only $3.70 Canadian. So yeah, there you go. Cool. Yeah. And, you know, I don't know. Maybe when we've had enough hexy hashy, maybe when we've had enough hexy hashy, we'll play Dwarf Fortress or something. That would be fun, right? Oh, is that true? Somebody just noted that on the table of content, or in the content, I may have forgotten to update all of the dates to 2021. That's possible. I'm pretty sure that I updated the actual days, but let's just check that to make sure. Bloop, badoop, badoop. I don't see any 2020s on here. Week of January 24th. Yeah, okay. Let me re-explain how this chart works. Just because it's a little bit on the confusing side, but it's still the best way. It's the way that I have chosen to do it. So that's how it's going to be done. So week 3 is the week of January 24th. If you take a look at your calendar, the first day of the third week of class is January 24th. So it's not exactly that this is the due date for the assignment indicated. It's actually technically the due date for the assignment the week before, right? Because all of the assignments are due on Sunday at midnight. So the first assignment will be due January 31st. January 31st, because you'll have the third week to work on it, submit it the 31st. Then next week is assignment 2, submit that on the 7th, etc., etc., etc. Hopefully that's clear for everybody. Doop, doop, doop. Yep, good. If I go to the full schedule option, it's in 2020. Well, if that's the case, then it's wrong. Yes, if you want to buy the pinball game, you're welcome to buy the pinball game, too. Twitch, yes. Well, I don't have a Twitch thing, you know? YouTube not having emotes should be a crime. Yes. Lecture distractions, yeah. Does my cat have a feature? No. Ooh, did I make the soundtrack? No. No, I have a friend who's an actual bona fide musician. He makes his living playing the piano. And he's a very good friend of mine, and we work together on the project. I'm really, really pleased with how the music came out on this one. We'll get to the lecture material very shortly, but it's very cool. I wrote a script for this thing where we have like a bank of 20 odd sound effects that are all different notes on a keyboard essentially, and we have a script that ensures that whatever sound effect is being played is always in harmony with the background music. So that's like, if you're aware, that's how the new Mario game, Mario Odyssey, that's how they did it, which is really cool. I recommend going and taking a look at some analysis videos on the internet about that, because it's really cool how they did that. Yeah, cool. So anyway, let's actually talk about some lecture material. We can have fun this afternoon, just as a, I don't know. Maybe I'll call it My Wife's at Work stream. So, last time we kind of got bogged down a little bit in the flowcharts. We only got through, I think we ended up on this slide. We only did 6 slides last time, but that was because I was showing you code, and you guys had lots of questions about code. I really don't mind spending a lot of time on this material, because this is of all of the material in the course, this is going to be, this is the most important material to really know second nature. You got to know this stuff like the back of your hand. So, yeah. So, yesterday we were discussing this example program which calculates the median or middle number of a set of 3 numbers. We had done that all up good. Let me just pull that up on the old whatever this thing is. MD3. What is this? This is winter code. Get it. Topic 1.py. As I said previously, you're perfectly welcome to use any sort of programming IDE that you think is useful to you. I'm using something extremely basic, if only to demonstrate to you, the viewer, that you don't really need anything fancy to be able to do this. All you really need is a text editor and a command prompt. If you download the Anaconda distribution, you can get the PowerShell version for Windows, which is essentially does the same thing. So, this is this guy in code, but I won't dwell on it too much. So with flowcharts, it is possible to do annotations on a flowchart itself. So, you know, often... Okay. So this is a really important thing to know about programming as well. It's kind of ancillary to this topic, but it's an important conceptual point that doesn't necessarily appear in the lecture slides. In programming, we often think about what is true at a certain point in the program. So, if statements are a great example of this. If you have an if statement, it is guaranteed that anything on sort of this branch of the if statement, this property will hold on this side of the if branch, and this property will not hold on that side. So very often when you're programming, you're concerned not only with what the sort of raw values of the data you're operating are, you're also interested in what can I say about the data at this point in time. You can actually bake into the functions themselves a lot of these types of ideas. For example, with median, there are a few implicit assumptions that we're making about what the inputs are to the median function. We are, for instance, assuming that these inputs are numerical inputs. Because Python is dynamically typed, you can actually put all kinds of different things in here. And if you do put all kinds of different things, particularly things for which less than and greater than operations are not defined, then this function doesn't even make any sense. Very often when we make functions, one thing that we do is we document takes 3 integers or floats as input. If you don't know what a float is, don't worry, we're getting to it in a few weeks. A floating point number is basically a decimal number, or a real number. So it's possible to keep track of all of these different implicit conditions that exist within the context of the program by documenting it directly on your flowchart. However, it gets messy quickly, and generally speaking, like, rare is the case where you'll be using a flowchart to design a program anyway. You'll typically just do it directly in code. So, what is the maximum number of operations required to compute the median of 3 numbers? If we are considering operations to be both the testing of the conditions and these assignment statements. Another way of saying this is, what's the maximum depth of operations on any particular branch? And of course, it's 1, 2, 3, 4. So that's the sort of thing. This gets into the idea of best case versus worst case runtime. So in the best case, we can compute this in 3 operations. In the worst case, we need 4. And you can see we have, 4 out of 6 of the possible branches are the worst case scenario. Why did we write m is equal to -1 at the start of the code? Kind of like as an error checking mechanism. If m is still -1 at the end of the code, we know something went wrong, and we can test for that with an if statement. Yes. So, here's another example. Flowchart for min and max. So, what are our inputs? We have integers ti for I is greater than or equal to 0 and less than n, which is a series of n temperature readings. We also have an integer n, which is greater than 0, so that's the number of inputs that we have. Our outputs are the minimum temperature min and the maximum temperature max. So let's do some coding. Def, what are we going to call this? Call this min-max. Our inputs are a range of temperatures T and a integer n. I'm going to show you guys, this is a little bit advanced right now, but I'm going to show you what a list is. A list. This is something we won't get to for a little while, but essentially you can have a collection of data inside of a programming language that you can get at by the various indexes. Very similarly to how, for TI you'd have T0, T1, T2. You can actually collect all of these things into one variable. We call it a list, and in this case we're going to call it T. We access the particular elements of that list by using square braces and giving it a specific number. We'll see how this works. So let's say we have let's implement the algorithm first. Comment that guy out. So first we declare I as 1. We declare min as t at 0. And we declare max at max as t at 0. So essentially what this guy does is it loops through all of the elements of the list. It checks each element of the list sequentially. If the new element that we're examining is less than the currently recorded minimum, we update the minimum to whatever this new value is. And correspondingly, if the new value is greater than the maximum, then we update the maximum to be the new value as well. Of course, it can't be the minimum and the maximum at the same time. That's just how numbers work. So, that's how that goes. So, in this case, we will be using a while loop. While I is less than n, if t at I is less than the minimum, then the minimum is equal to ti. Otherwise, if ti is greater than the maximum is equal to ti. For those of you who know how to code already, you may be noticing a stark lack of semicolons. There are no semicolons in Python unless you want to group multiple statements on one line. And then, of course, the most important part, the thing that makes this loop not run infinitely, is I is equal to I plus 1. If I never changes, then this loop will I will never be greater than or equal to n, so this loop will just go forever. And then, this is another neat little Python trick. You can return more than one thing from a function by using a comma. So, let's say we have a set of temperatures, -1, 4, 5, -12, -8, -7, -7, plus 13. Sure. N will be 1, 2, 3, 4, 5, 6, 7, 8. 8. There are 8 elements in this list. So, I'm going to do this. This is like using only the most basic constructs. There are more efficient ways of doing this particular algorithm, which I will show you in a moment, but I just want to show you like what the absolute direct interpretation of this flowchart is first. Then after we verify that it works, then we'll start optimizing. So, let's run it. Min, max, t, and n. Let's make that capital N, just to distinguish the actual parameters from the formal parameters. And then we'll have to print it. Cool. All right. Python 3, topic 1.py. There you go. So, the first element returned is the minimum, so that's -12, and the maximum element is +13. There you go. Now, we can do some things to be able to view what the intermediate values are inside of this algorithm as it's executing. So you can actually use print statements within these guys. So print min is equal to, and then I think you can do it like this, min. This might be a syntax error. I don't know. Last semester I was doing so much C. It was like the worst thing ever because I was confusing my C code with my Python code, and like they're just similar enough to be annoying when you get it wrong, you know? So let's see if that works. It does. So, on the first loop iteration, I is equal to 1. Min and max are both equal to -1, which is this guy. I is equal to 2. That's 4. That's greater than the current maximum, so the maximum is updated. And you can see that it just goes through each iteration and eventually arrives at the result. There you go. The last iteration is not being shown here. It would be if we moved these print statements to the end after everything had been processed. Coolio. Oh my goodness, that's a lot of... Oof. So, why do you define things? So, it's like this is how you write a function. Like, theoretically, you could just take this function name away, right? And you could, you know, unindent all of this stuff to the basic level and just run it once. You can totally do that. The problem with doing that is that means you're lacking the very useful abstraction method of taking a segment of code and packaging it up as a function. It's a very useful thing to do, and it's required for all of your assignments, so you best get used to the idea. Well, no, you can invoke the Python interpreter from PowerShell. That's what I mean to say. Aren't min and max reserved keywords? Yes! So, someone actually knows a little bit of Python here. Yeah, technically speaking, what I'm doing here, see how these are highlighted in blue? Min and max are actually technically functions that are predefined in Python, but because I'm using them, because I'm assigning things to them inside of this context, within the context of this function, I'm actually overriding the inbuilt definition of min and max to be whatever I want it to be. So, I should put the microphone over here. Maybe that would help. Interesting. All right. So, because the I don't know. Is that too much in the screen? It is very in the screen. How about that? Hop, hop, hop. That's a bit better. So what's happening here is... What was I talking about? Yeah, so min and max are reserved keyword. Well, they're not reserved keywords. You can't over-define, like, you can't overwrite the definition of something like if, or while, or def. But you can do some other things, like min and max. Well, if n is not defined, then you should define it. Why am I allowed to have an if statement without a corresponding else statement? Because the else statements are optional. If you have an if statement, that's actually a really good question. So you see how in this sort of substructure here, the no branch just sort of joins back up at the end? That means that the else branch does nothing. You could, in theory, put it in explicitly if you wanted to. You would have to write this, else pass. Pass is Python's word for don't do anything. However, it's redundant. It doesn't have to be in there for the program to make sense. So we can just omit it. We don't have to include it. I could also learn how a keyboard works. That might help. Yeah, that doesn't have to exist. Yes. Why is one variable lowercase and the other uppercase? We'll get into this when we talk about function parameters, but I'm trying to draw a distinction between these, which are called the formal parameters, and these, which are called the actual parameters. So they do not have to be named the same thing. I could name this splort, and as long as I was consistent up here, the function still runs fine. In Python, it's the actual value that the variable contains that is given into the function, not the variable name itself. So it's this guy that's getting passed. You can think of it as being a substitution operation. So there you go. Why is I 1 instead of 0? Because in Python, things are 0 indexed. So if I have a list equals 1, 2, 3, 4, 5, 6, you would think that if you wanted the first element, you would go L at 1. But that's not what happens. In programming, the first element is L at 0. This is called 0 indexing. Pretty much every single programming language does it this way, and it has to do with the way that memory is addressed inside of the computer. Like, it has to do with technical things way down in the computer. If you're using MATLAB uses 1 indexing instead of 0 indexing. But any, like, proper programming language, MATLAB is not a proper programming language, despite what the MATLAB people claim. Well, I mean, there's a proper programming language that's, like, technically... you can do proper programming in MATLAB, but, you know. I remember back when I was taking calculus, there was a professor who said something that I will take with me to my grave. He said, when your face is itchy, it is possible to scratch your face like this, but sometimes it is better to scratch your face like this, and that's one of those situations. Okay. What does t at 0 mean? That means the first element of t. So t is a collection of data, right? This is the first, -1 is the first element of t. But you get at it by providing a 0. So maybe this, maybe we'll, let me show you this. So while, let's say, I is equal to 0, while I is less than the length of splort, print splort at I. See, I forgot to increment it, so that's what an infinite loop looks like, by the way. Just negative ones forever. I gotta provide the I is equal to I plus 1. There we go. There. So you'll notice at the top, these are all of the elements in the thing. I can make it maybe a little bit. This is dumb. Let me just replace this back for T. There we go. So let's say T at this is just to make it look pretty. Don't worry about this right now. I'm performing string conversion so that it prints properly. See, T at 0 is -1, T at 1 is 4, T at 2 is 5, -12, -8, -7, -7, and 13, which are each of the elements that are included in the data structure. So there you go. Yes! Oh my goodness, he was awesome. I forget his name. Yeah. So yes. So if you have I starting at 0, and every time the loop happens, I is incremented by 1, eventually it'll hit the length of the array, no matter how big the array is. This is actually one of the optimizations that I was going to show you up here. But, you know. Yeah. Good. So, here, I'm not sure I should proceed with the optimizations, because it might just confuse you. But, well, you know what? So, take this as, I don't expect you to be able to do this yet. This is what programming can look like if you know what you're doing, right? So, first of all, if you can compose these guys into elif. This means else if. So that's like a common construction. You can just smack those together. You can replace this while loop for a for loop. So for element in T, and then you would replace all of the instances of Ti with E. For loops are extremely handy in Python. I recommend getting familiar with them. It's very difficult to get yourself into a situation where you have an infinite loop in Python if you're using for loops. Oh yeah. Okay, so on the slides, that's what everybody's talking about. So the reason I starts from 1 here is because T0 has technically already been examined, so you don't need to examine it again, right? It's a redundant step to say, oh, is T0 less than T0? Why, no, it's not. It would just, it would not do anything useful, so they started at 1 instead of 0. But typically, it's typical to start a loop at 0 and go through every single element in the array, even if 1 or 2 of the cases are redundant. It just makes it easier. Easier to program. And of course, then there is the definition of min-max for smart Alex, which is return min t max t, because min and max are functions in Python that have already been defined to do these operations already. So, what we did in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 lines of code that were useful and not print statements in 1, that got reduced to 1, 2, 3, 4, 5, 6, 7, 8, and then to 1. And if we demonstrate this, we'll see that each one of these produces the same result. I'm just going to get rid of these print statements. Oh, I've got a syntax error. Pardon me. Missing a colon. Right there. Oh. Right. So I didn't need n anymore, so I got rid of it, but I need to actually do that there as well. There you go. See? All three calls to all three versions of that would have the same return result. What's the difference between for and while loops? If you're patient with me, we'll actually get there. Where we have a reasonably extensive go through of that in the coming week. Am I still? The video seems frozen. Oh, is it? It was just not running. Okay. Gotcha. Does it make sense to say I represents each t value? In a sense, yes. We call I the index. So it is indexing the loop. We're going to get it. We're going to get there, though. If you don't get all of that, don't worry about it. We're going to explore these ideas. We're going to tease this stuff out. Right now, I'm just trying to show you, like, I'm trying to show you real programs, you know? Or, you know, at least these funny little examples we have in the slides. It's very important to me that you guys see code. So, there you go. Basically, anytime you're working iteratively over a data structure, you should be using a for loop in Python, for those of you who know what that means. When I say iterative or iteratively, what I mean is loops and looping. To iterate is to run one go-through of a loop. We don't really have to talk about this slide because I already demonstrated it in actual code. Though these are not interesting questions. It's, again, this analysis of how many times would you hit a particular condition if you were to go through it like this. Not a particularly useful analysis in my estimation. So, let's talk a little bit of more of the sort of soft details. Let's what's it called? Provide motivation for computers. I don't think I really have to motivate computers, actually. Pretty much all of you should know to what degree computers form a vital role in our lives. So, programs are algorithms that can be executed automatically by a computer. Sure. Fixed program computers serve only one purpose. So, some of the early programs, or some of the early computers, how it worked was your computer did one thing because it was made of electronics, and the electronic circuits had one purpose, and it served that purpose. These are fixed program computers. These things still exist. Anywhere you would have, like, one of those little green chips with the black-looking rectangles on them, which are, like, computer chips, or computer boards. If you take your kitchen timer and you crack it open, and you take a look at the circuit board in there, what you see is not going to look like a standard computer, not like a laptop, right? It's a very, very miniaturized thing. What it is it's a custom-built circuit that performs one type of calculation. Technically speaking, it's a computing machine. That is a computer. However, it only runs one program, right? If any of you are eventually going to go on to embedded systems design, that's the type of computer that you will be designing and making. It requires knowledge of electronics. Stored program computers are... that was a big innovation, because suddenly a computer wasn't just doing one calculation, it was executing instructions. In the first few iterations of the computer, these instructions were stored in various different types of ways. On some of the very early ones, you had like dials, like vast banks of dials, and you had to set the dials to particular positions, and that's how you entered instructions. In later iterations, we had computers that would take punch cards. I think I have a picture of a punch card in here. Yeah, this is a punch card. See this guy right here? This used to be how you would program in the 60s and 70s. These guys... So basically, in order to write a program, you would need a whole stack of cards. You would punch holes in the cards in particular positions, and the computer would read the positions of the holes in the cards and interpret those as instructions, and then it would execute those instructions. This is like in the era of computers before monitors existed, like before like displays, right? Like when you would get output from a computer like in binary on a ticker tape, kind of similar to a telegraph machine. Anybody who watches old movies, you should be like, I know what that is. Or even movies about the olden times. So the idea that a computer could store its own program became like that was a huge innovation, and we owe this idea sort of it arose in a few places at once, but it's generally credited to a Mr. Alan Turing, who is to computation what Einstein is to physics. Alan Turing is like he is the giant on whose shoulders the entire discipline is built. If anybody is into movies, there's a movie called The Imitation Game, which is a biographical. It's like a bioflick about Alan Turing and all of the various challenges he faced in his life, including defeating the Nazi Enigma machine. It is not an underestimate to say that if Alan Turing hadn't been working on the Enigma machine and had broken the code by actually implementing his idea of the universal machine, then, we could all be speaking German right now. That innovation was of key significance during the war, because what it allowed the Allies to do was to conduct a misinformation campaign where they were able to sort of misdirect the Axis powers about where the D-Day landings would be. So the Germans were they thought they were landing on one beach, and the Allies were landing on a different beach, so the Germans built up their defenses on one beach so the Allies could sneak in around them because they were misdirected. It's very cool. So yeah, anyway, Alan Turing, very cool. This is what a computer used to look like back in the day. Computers used to be the size of rooms. It's really cool. So from punch cards, we then get we get the development of solid-state electronics, essentially, which is to say transistors. And I won't go into the details. I'm not going to test you on any of this or anything. It's mainly for your own interest. But before the development of solid-state electronics, you had essentially what were called vacuum tube transistors. So in order to build an electronic switch that could operate reasonably quickly, you had a thing that looked a little bit like a light bulb that you would plug in, and these things would burn out, and they were about yay big. So you can imagine, the modern CPU has like billions of transistors in it, billions of these tiny little switches. So you can imagine how the sheer scale of things would limit the size, like the size of the computer would become so big and its computational power so small because of the size of the components, right? So eventually we developed solid-state electronics, which means that we can do these on silicon wafers, right? We got these little tiny pieces of silicon that if you add specific atoms to them during the manufacturing process, they have they have native electrical charges, which allow them to block or allow the flow of electrons in the same way that as a switch does if, certain other parts of the silicon are at high or low voltages. So high or low voltages here being 0 or 5 volts. So about what you would get out of three AA batteries wired up in series. So in essence, because we developed solid-state electronics, this allowed for the existence of the so-called microcomputer, which only really became popular in the 1980s. It's sort of, in the 1980s, things became, like, the microcomputer became miniaturized to the point where it was sort of a viable consumer good. Before that, computers were mainly, like, these stored program computers were primarily things that institutions would have, like NASA or a university. Things like the little Atari console that you would have played with your friends in the 70s. These were actually examples of fixed program computers a lot of the time. And in fact, like the cartridges that you would have put in an Atari, that was also a fixed program computer. These things were like actual electronic circuits in a lot of cases. Although things were sort of moving in the direction of stored memory and that sort of thing at that time. I might be wrong. It might be the 70s that this stuff was happening. Anyway, that's not important. What's important is that all of computation now, like now we're getting to the point with transistors where they are literally atoms across, right? The processor is that is the most complicated and smallest thing that human beings have ever developed, and they're so cool and rad and, like, man, like, it's very interesting. Science fiction from the 1940s and 50s completely missed the boat on the development of microcomputers. It took everybody by surprise, these things, and now they basically rule us. So there you go. Anyway, so this sort of gets into the idea of how is a computer actually designed. So you've probably heard the term CPU. That's Central Processing Unit, right? The Central Processing Unit is the thing that actually executes all of these instructions. When we write programming, we are composing a series of instructions. These instructions are being executed inside of the CPU. The instructions are also telling the CPU how to interface with the memory. Memory in a computer is stored externally to the CPU. You guys will all know this because, if you have memory chips, like RAM chips, like everybody knows what a RAM chip is, I hope, you can plug those in. That gives your computer more memory. You can't download more RAM, contrary to what the memes tell you. But yeah, essentially, this is called the von Neumann architecture, and this is the most prevalent style of architecture that exists in computers today. There are other alternative architectures that are used primarily in like the embedded system space with FPGAs and that sort of thing, but this is the basics. It takes input, it processes commands, and it produces output. This is what a computer is. That's why we say garbage in, garbage out. If the input is bad, then the output will also be bad. It is not reasonable to expect a computer to fix your mistakes. Even spelling programs, which the spell checkers, which the ostensible purpose of a spell checker is to take your garbage sentence and produce a less garbage sentence. It depends on how much garbage the sentence is. If the sentence is such garbage that it's not even, like, recognizable English, the spell checker is not going to be able to do anything with it. Right? Garbage in, garbage out. So anyway, that's a bit about computers. It's now time for your next class. I will answer some questions from the chat. Yeah. Yes. Yeah, the imitation game was, I'm making... Oh, I don't want to make you cry. Don't worry. If you're worried about the course, don't worry about the course. We start off... Like, I know I'm throwing so much information at you all at once, but that's just because I'm an excitable person, and I get so excited about computers. Just try some stuff. Like, try a few coding bat problems. When we get into assignment 1, you'll see that assignment 1's really not that bad. We are going to move you gradually into all of this information. Please don't panic. Don't drop the course just yet. Give it another week or two and then drop the course. Human ingenuity is... I've not heard that, yeah. Or, yeah, that maybe that you're not talking about a movie. Maybe you're talking about, like, human beings and how cool we are. Human beings are pretty cool. Oh, yeah, if you want a demo of that, it's like, where's my interpreter? Python 3. S is equal to input. How many fingers am I holding up? How many fingers am I holding up? 4. S, 4. That's how you get input from the user. Don't code bad. Yes. That is the moral of the story. Oh my god, yes. Holy smoke, yes. I guess I could instantly produce an appreciation for Python in you guys by showing you even a small amount of C++. It was actually a Polish mathematicians who broke the Enigma code and lended their findings to Brits to further development. Ooh! Very cool. I didn't know that. So that's the fact that Turing broke everything, that's like Hollywood magic, right? Man, the Poles. The Poles are awesome. Do you need to install virtuenv to use Jupyter Python? No, but I would recommend Anaconda. Instructions in the syllabus. Yeah, I could do that about, I could do that in the stream. I could do the process of making the game. Like, it's... I can only reasonably expect like 10-15 minutes of the actual game to be, you know... It's just a puzzle game. I don't think it makes good streaming, but, you know... Drop it after you don't get the refund. Yes. Yeah, I know. Yep, I don't know. It's just my style. Assignment 1 has not been released yet. Yeah. Don't worry about it. We'll make an announcement when things are ready for you guys. Oh, okay. Turing improved the pre-war Polish solution to breaking the Enigma code. Ah, there we go. All right. That is the marriage of those two stories. When is Assignment 1 going to be released? We'll probably release Assignment 1 and the practice assignment at the same time. Cool. Okay, so, yeah, cool. Well, certainly, yeah, certainly they built the computer, so, you know, that alone. Swift? To be honest, I've never used Swift. I've heard it's good. But yeah, I haven't ever used Swift. Yeah, so sometime this afternoon I'll do a I'll do a dev stream. Oh man, throwing some shade. Yeah. Yes, have fun in have fun in It's like, Swift sucks. No, it's the best. Objectively not. Objective C. For all you Mac users out there. For anybody who doesn't get our programmer in-jokes, don't worry about it. You don't need to get them to pass the course. Oh, well, there we go. We have reasoned and calm debate over what programming language is best. Obviously, Haskell is the best. Yeah. It's said about Python that Python is everybody's second programming language. Yeah. Anywho, I'll just hang out for a minute or two longer, see if there are any questions related to the course. Maybe there's one I missed. TypeScript. No. Python is Java, but less dumb. Oh, my goodness. What are other data types except string? Integer, float, boolean, and then you have the compound ones like list and tuple. String is actually a compound data type as well. Technically, it's composed of characters, although Python actually tries to hide the fact that strings are made of characters from you for some gosh darned reason. I've never used it. I'm not going to fight you on a language that I've never used. You know, I actually like C. Like, I know it's clunky for practical applications, but I love the semantic elegance of C. I love how C is like 2 steps away from assembly. I love that about it. It's like, if you really want to know how your computer works, you learn C. And then if you know C and you want to be able to program practically, you then learn C++. Yeah. What are all the languages I've used? Well, I've used a fair amount of Python at this point, but I only really started using Python when I started teaching this class. So, you know, but I've been using it for a few years now. All my game development stuff I do in C#. Back when I was in high school, I used to use ActionScript. I used to do stuff in Flash. Flash is dead now. Yeah, C is really good for learning data structures. Ha! Yes! Learn assembly! I've used C. I haven't really used C++ very much, although I did a few slides on it, a few slide sets last semester. Should have made Hashi in assembly. No. I did my thesis in Haskell. Haskell is actually a really, really good language if you can if you can manage the abstractions. It's like nothing you've ever tried before. Yeah, I'd say that about rounds it out. Yeah. Yeah. Yeah, if anybody's interested in C as a programming language, since it's been mentioned, there's a bunch of all my lectures from last semester are still up. So, you know, if you don't have enough classes this semester and you want to take one without getting any credit, you know. But yeah. Anyway, I'm gonna go have some lunch, and maybe in a few hours we'll have our fun stream of fun. Haha. Take her easy, folks. Good luck on your chemistry class. That one guy who was already at his or her chemistry class.